So the collections framework is essentially about data structures and how we want to organize our data structures within object-oriented programming, specifically within Java. So the collections framework is a unified, generic framework for the representation and manipulation of groups of objects. So it's unified, so when they created the Java programming language initially, they didn't have the collections framework. There were a number of different data structures that you could use. They were not related to each other, and you could use them for various tasks, but it wasn't very clear which to use when, and they had various problems associated with them. So then a few years later, they developed this collections framework, and it created clearer data structures, and the data structures have a lot of support with them, a lot of utility classes, which we can use today. So it's a unified generic framework, so it makes use of generics, which means that your collections are strongly typed. So Java is what we call a strongly typed programming language. The compiler will check things for you. It checks that the right type that you want to create is actually instantiated at runtime. Initially, when the first data structures were developed before collections, they did not use generics, which means you could have done things like created an array and placed in it any object. And therefore, when you actually come to run your program, any object could pop up within the runtime environment, and it wasn't very clear what objects were contained within your arrays. So by applying generics, we can now specify exactly. We can say things like this array is only an array of persons, for example. And by specifying that, the compiler will tell you if you try to put something other than a person within your collection. So it helps you maintain that aspect of Java, which is a strongly typed programming language supported by the compiler, checking this type of error for you. So that's the main reason why we have generics. So it's a unified generics framework for the representation and manipulation of groups of objects. Manipulation is dependent of representation, and that means that we're making use of interfaces, as we've seen in several of the examples we've looked at previously. So it includes interfaces that define types of collections. We've got abstract implementation for customization and for any general code. We've also got general purpose implementations. So these are some of the legacy implementations, so other implementations for legacy vector and Hashtable. So these are the old data structures that I talked about before. So generally, you're not recommended to use vector and Hashtable. However, they're still supported because there's still a lot of legacy code out there which uses them. So just so you're aware that they exist, if you come across a piece of code that uses vector and hash code and Hashtable, then all you have to do is look at the API and look at how they're implemented to figure out what to do with them. So you've got some other implementations you need to be aware of, and we have utilities to operate on collections and arrays and provide algorithms. So there's a big host of things that are common to data structures that we want to be able to do, and you can either implement them yourself, or you can make use of the collections framework and all the utilities that it already provides for you. So because these tasks and algorithms are used over and over and over, Java decided to just solve them for you and put them within the collections framework, and you can just go ahead and make use of them. So you've got utilities for sorting, for searching, and various other things as well that you can do. So if you want to look in detail at the collections and generics APIs, then you can find them at these links down here. So this is the general structure of the collections framework interfaces. So it's a number of interfaces which sort of are linked to each other. And here you've got the key interface, which is our collections interface. And it is extended by a number of other types or other interfaces. So these are all interfaces here. So we've got the key ones, which are the list interface and the set interface. So a list is kind of a sophisticated type of an array. A set is a data structure with no duplicate items. So if you want an ordered list of items with an index, you would usually use a list. If you don't care about the ordering, then you want the data structure to automatically get rid of any duplicates, then you might want to use a set. You've also got the idea of a queue. So it's kind of a first in, first out data structure. You've got here a sorted set. If you create a set and you want it to be sorted, then you make it implement the sorted set interface rather than the set interface. And here you've got a couple of data structures that make use of the collections framework. Some developers consider it to be part of the collections framework, others consider it to be separate from it, but essentially it is part of it, because in order for it to function, you have to use the collection. It does use the collections framework, and a map essentially uses both the collections framework and the set, which extends the collections framework. So the keys within maps need to be unique. The ideal data structure, therefore, to hold all the keys of your map is to use a set, because the set guarantees uniqueness of your object. So, but the values they don't need to be unique. So you can have, so each key has a value, remember, and the values can be implemented using any data structure. So we're using sets for the keys, and we're using the collections framework for the values within the map. So collections extend an interface called iterable. It's basically an interface which provides a very, very common thing that we need to do with data structures, which is the ability to iterate over or traverse a data structure and perform certain functions on it. So, so instead of creating your own while loop, for example, that does something like maybe remove one of the elements of the data structure if you fulfill certain conditions. So you go over each element within the data structure, you check each one, and for example, let's say you want to remove element number 3. So you could implement that yourself, but there's a problem with that. It's not very easy to do, because you need to re-index all the other data structures. Maybe you need to create another data structure to copy all the elements into the new data structure. So it's a complex thing to do. So what they've done, they've created an iterable interface that does that for you. And we'll see how that's implemented in an example in a little bit. So we've got the collections framework here. It extends the iterable interface. You might want to return the size of the data structure. How many elements is there? Is it empty? It'll return a boolean true or false. Does it contain a certain element? It returns true or false. You can also, there's a number of methods which labeled here as optional. So by optional, it still needs to be implemented because it's an interface, and in order to adhere to the interface contract, remember, you have to implement all of the methods within the interface. But what you do is, in the implementation of the method, you just throw a method non-supported exception. Okay, so that's the idea. You just you put the signature of the method within your class, and you just throw this exception that we're not supporting this method, and that's fine. You're still adhering to the contract, because you've put it within the body of your class, but you're just not putting any useful code within the body of the method. So let's see what's the commonality between those methods. So you've got an add method here, so the ability to add something to your data structure. You've got a remove, removes an element. We've also got add all, remove all, retain all. So the idea is that there are some data structures you want to create, that you want them to be created and then to be non-modifiable. So you want them essentially to be immutable. In that once you've created them, let's say for example you want to create a collection that has the days of the week. So so Monday to Sunday. So once you've created it, you don't want anybody to be able to add any more days to it or remove any days from it. So so that's a kind of a collection that maybe you want to be unmodifiable. Okay. So in that case, you don't want to have those methods: add, remove, add all, remove all. You don't want to have those at all. They're just not useful, and you just don't want them. So you just put them within the body of your class, and you throw a method not supported exception if somebody tries to execute them. So so add will return a boolean true or false if you successfully were able to add an element or not. Remove will do the same. So what other methods do we have? You've got here the iterator method. So if you want to iterate over your objects, then what you do is you call this method, the iterator method, and it returns an iterator object on which you can traverse, and you can do various things with your data structure. So we'll see an example of that. So other things you can do, you can check if your collection contains another collection. So does my collection contain the collection of these items, true or false? It's able to add a bunch of elements as well. Remove all, remove this collection from my collection, and retain all basically means that retain everything in my collection except those elements, except these elements here. So clear just empties it completely. You can convert it to an array, or you can convert it to an array of a particular type. So you can specify I want to convert my collection to an array of a particular type, and you can do that as well. So yeah, so here's the example of the iterator method and how you would use it. So I just want to talk about the iterator method a bit more. So collections have an iterator method. It returns an iterator object. So we have three methods within iterator. These are hasNext, next, and remove. And this is sort of one of the main reasons why the iterator interface was created: the ability to remove objects easily from your interface when you need to do that. So here's an example. So I'm creating an iterator object, and basically the way you return the object is you call this method on your collection. So you say my collection dot iterator gives you the object. So this is the object that we have now. So while there is an next element within my collection, then call it and do something with that object, whatever you want to do. So so here's an example down here. So we've got a data structure of files, and we're saying while it has next, print out the details of that track. So that's a very simple thing that you may want to do. So I'm just going to have a look at some of the main data structures within collections. So remember I mentioned that a set is a collection that has no duplicate elements. So it's a data structure where no two elements, E1 or E2, such that E1 equals E2. So there cannot be any two objects within your data structure that satisfy this relationship. Okay, otherwise you break the set rules. It's not a set anymore. And there is at most one null element. So you can have one null element within your set. So there are no additional set operations. They are the same operations within your collections framework, whereas we'll see that some other data structures do have some additional operations. Yeah, so there are some additional constraints, however. So the add operation returns true if the collection is modified as a result. So the set add operation returns false if the set already contains the element. So when you try to add an element to the set using the add method, if it already exists, it can't add it because it's already there, and it'll return false. So this add method here, there's a Boolean operator in order to do that. So this maintains the semantics of the collection operation and adds a reason for the operation to fail. Also, set constructors enforce set semantics. So if you try to add a data structure to a set through its constructor, the constructor should also enforce that rule. So it'll automatically check if there are any duplicate elements you're trying to add into the set. If there are any duplicates, then it won't allow you to create that data structure. So yeah, so no duplicate elements in a set instantiated from another collection. Okay, so if you try to pass in another collection, it'll check everything. A list, on the other hand, is an ordered sequence of objects that may contain duplicates. The user has control over where the elements are inserted and can access elements through their index or through their position. So the list interface extends collection and defines additional operations to work with indexed elements. So for example, we have a list specific iterator, and it's a bit more sophisticated than the normal collections iterator. So whereas the normal collections iterator always starts from beginning to end and can only go in one way, so you do iterate and it'll go from start to finish of the collection and do whatever you want to do, remove elements or list them or whatever. The list specific iterator can start from any index point, so you can say start the iterator if you like from point number 10 and iterate backwards to number 5, or you can go forwards from 10 to 15, for example. So you can do specific operations with the list specific iterator taking advantage of its index, essentially. So the list specific iterator supports iteration from user specified position. So list actions relative to an iterator position and both forward and backward traversal of a list. The map is something that we've seen before. So we've got a set of keys. So this is a set, meaning that each of these should be unique. Okay. and we've got a collection of values, meaning that it's a collection, it could be a list, it could be any data structure, and they don't have to be unique. You cannot have duplicate keys. The collection of keys is a set, and the main operation to add elements to your map is map, put, key, and value. So this replaces any existing entry in the map that has the same key. So one or more keys can map to the same value. So here's an example where you've got this and this are mapping to the same value. So for example, you might have two people, you might have a data structure where you've got people and their addresses, so you might have two people that live at the same house, for example. So that's why, so that's an example where that will be useful. So this is what the map interface looks like. These are some of the main methods that you have in there. So you can put elements within your data, within your map. You can get an element based on the key value. You can remove. You can check whether or not it contains a particular key. You can check based on the key, or you can check based on the value whether it contains them. You can return the size. You can check if it's empty. You can put all, so you can put a map into a map essentially. You can have a bunch of items added in. You can return the key set, so you can return a set of all the keys, and you can return a collection of all the values. And you can also return a set of the entire map. So when you've got a data structure, one of the main things that you might want to do is sort it. So you want to be able to order the elements within your data structure from smallest to largest, largest to smallest, or by the alphabet. And one of the key ways that we do that is using the comparable and the comparator interfaces. And remember that two key design patterns that we use for that are the mixin design pattern and the strategy design pattern, depending on whether or not you own the data structure or not. So if you own the data structure, then you'll use the comparable interface in order to order your object. If you don't own it, then you'll use the comparator one. So both interfaces have methods that return an integer value to indicate the relative ordering of two objects, and the value is negative if the first object is less than the second object. So if you're comparing letter A to letter B, then it should give you a negative value, so that you know that you need to put A before B. It gives you 0 if objects are equal, and positive if the first object is greater than the second object. Obviously, implementations of comparable or comparator need to be consistent with the equals methods. So then you need to make sure that they're consistent with each other. So any variables that you're using to determine whether or not two objects are equal, you need to use those same variables in order to compare whether one or object is larger or smaller than the other. Yeah, so there's a tutorial on that if you want to look at it in detail here. So now that we've looked at the main interfaces for data structures, so what are the main implementations of those data structures? So we've got the collections interface, we've got the set interface, we've got the list, we've got the queue, we've got the map. So these are all interfaces, but we need some kind of concrete way in order to implement them. And most of them have more than one option. So at the top here, at the top part of this image, you've got collection, set, list, sorted set. There's an extra one here called random access, which we'll talk about in a little bit. And we've also got iterable. So we start from the left-hand side. So our set interface has got an abstract set, and we've got two concrete implementations. We've got a TreeSet and a HashSet. So the default implementation that you will use mostly is the HashSet. But if you want to have an ordered set where the elements are ordered, then you can use a TreeSet. The default we say that you always use the default is because the default uses less resources generally. Ordering items in a set or any other data structure takes more resources, more CPU and more memory. So unless you want things ordered, then use a HashSet. If you want things to be ordered, then use a TreeSet. So for the TreeSet to operate correctly, it implements sorted set, okay, this has some additional operations which help to order the items. And then you've got on the right hand side here, we've got our list concrete implementations. So in the middle here between them all, we've got an abstract collection. Okay, so the abstract collection has some common methods between all the data structures, so it has some common code between them. And then, so for the list, we've got an abstract list, and our concrete implementations are the linked list and the array list. The array list is essentially ordered by indexed. A linked list is ordered in a different way. So there's no index for the elements. They just sort of hold hands with each other. So we'll look at what a linked list look. So we'll look at the difference between an array list and a linked list in the next few slides. But notice that the array list here implements an interface called random access. So within a computer, all memories is what we call random access. So if you want to access any element in memory, whether it's element 0, 1, or whether it's element 1000 or 1 million, the CPU is able to access those elements immediately by their index and grabs whatever's in memory in there. So that's called random access memory. It doesn't matter, even if it's got a high index, that does not mean that it's slower to access that particular element. It uses the index and it knows exactly where each element is within memory. The same applies to the array list. Because it has an index, the array list can jump to any element. It can jump to any element and access that element in equal speed. So it doesn't matter if the array list index is 1 or 1000, it can get the values of those elements in exactly the same amount of time. So that's basically what we mean by random access. And this random access interface provides facilities to support that. So this is our map concrete implementations. So remember that a map uses a collection and it uses a set for its, so it uses the set for its keys and uses the collection for its values. So we've got an abstract map and we have concrete implementations which are HashMap and TreeMap. And it's the same principle applies. The HashMap is an unordered map, so the elements are unordered. A TreeMap, the elements are ordered. So these are the main implementations that you need to be aware of our main data structures. For a set, these are HashSet by default. If you want them to be ordered, then you use a TreeSet. For a list, an array list is by default what's used mostly, but you can also use something called a linked list. So we're going to look next at the performance differences between these data structures, so you'll get a better idea of when to use each one. And we've also got the map. The default implementation for that is HashMap, but if you want it ordered, then you would use a TreeMap. Another name for an array list is a resizable array. So you might see it's called a resizable array or an array list. And essentially what an array list does is it's a sophisticated type of an array. So you can create a simple array for any type that you want. But the problem with arrays, so when you create just a simple array, it's got a static size. You can't change its size anymore. So if you want to resize the array, increase its size, the way you do it, you have to manually create another array of the same type, and give it the extra size that you want to give it manually, and then copy all the elements from the initial array into the new array, and that's how you resize it. And essentially, this is what this array list does. It does all that for you automatically. So instead of using a simple array, you can use an array list, and it automatically resizes itself whenever the need happens. So everything happens in the background. It creates a new array if it needs to be, copies all the elements. So this is all happening in the background. You don't have to do it within your code. It's just happening within the runtime environment. So that's fine. That's great. But what it means is that its performance is dependent on how much you're constantly resizing it. If you keep adding lots of elements over and over to it, it has to resize itself all the time. So there's a slight performance hit for that. So we'll talk about that next. So a big O notation, the standard way to express this is this way. So you say O1, for example, and that means that in order to do something, it's taken one operation in the CPU. Okay, so O1 is the smallest, the fastest operation that you can have in when you're measuring the performance of anything that's happening within your computer program. So O1 is basically means it's taken one operation to do this. So whenever you add a value to your data structure, it's taken one operation. Okay, so adding value 0 takes one operation, value 1 takes one operation, value 3 takes one operation, this takes one operation. Then you come to, so let's assume that the size of your array is 4 only. Now, what the array list has to do, remember, is resize itself. So it needs to create a new array, copy all the elements over, So that's more than one operation. It's several operations. So let's say it takes 4 operations to do this, and therefore the array size jumps from 4 to, I guess in this case it's jumped to is that 6 or 7? It's jumped to 7 elements. Therefore, what's happening when we measure the performance of adding elements to an array, we have to take that into consideration. So what we do is we add these all up. So 1 plus 1 plus 1 plus 4. So that gives us an 8. And you divide it by the number of elements within your array list. So here, in that case, you've got, so let's say it's 4 just to make it easy. And that gives us a performance of 2. So the performance of our array list is 2. And we call that amortized time. So the performance of adding elements to your array list is not exactly O1. It's a bit higher than that. It's O2. Okay, so that's what we mean by amortized time, and it differs depending on what's happening in the background, how many elements you're adding, how many operations it actually takes to resize the array list. It's a very small number. We don't really need to know what that number is. We just need to understand the concept of how it's being created. Okay, so let's have a look at these numbers down here. So a resizable array of values that is reallocated as it approaches capacity. Okay, so common operations that are get. So if you want to get the value of any element, remember it's random access, just like memory is, so it happens immediately. So getting, setting as well, you just jump to the index and you set the value of the element. Again, it's very fast. Removing at tail, all of these run at constant time, or 1. So that's the best performance that you can have. Adding at tail runs an amortized constant time. So that's what we mean by OM here. So whenever you want to add an element to the tail here, it's sometimes 1, but sometimes it's a bit higher. So we take the average of that, and whatever that number is, it's a very small number. So that's what we mean by amortized constant time to add M elements. So removing at head is what we call, so adding, removing at head run in what we call linear time. So if I want to add an element here, the problem with adding to the head is that you need to re-index all the other values. So by adding an element to the head, basically what you're doing is you're giving it index number 0. Therefore 0 now needs to become 1, 1 needs to become 2, 2 needs to become 3. So that all takes time. So that's why it's the performance is linear time. So the performance depends on the size of the array. If you add an element to the head of a list of size 10, then it's going to take 10 operations, because each of those 10 elements need to be re-indexed. If it's 5, then it takes 5 operations. If the size of the array is 100, then it's going to take 100 operations. So if you've got some kind of a problem to solve where you need to add elements to the head quite frequently, and the size of your data structure is large, like hundreds or thousands of elements, then you probably don't want to use this kind of data structure, because it's just going to slow down your program significantly. So you might want to think about using some other type of data structure for that. Yeah, so adding or removing at the head runs in linear time, so that means ON for a list of size n. Insertion or removing elsewhere, so if you want to insert something in the middle, so the same thing applies. So let's say you've got this data structure here, and you want to add something here, then these elements here are all fine, but you still need to re-index all of the ones that come afterwards. Okay, so insertion, remove, and elsewhere is, so it's O1 to get there, and then an average of n divided by 2 to rearrange the list on average. Okay, obviously it depends on where you're inserting it. If you're inserting it very close to the tail, then the performance is going to be very good. It's going to be a small hit. But if it's closer to the head, then it's going to be a bad performance. So, but we say on average, inserting any place other than the tail or the head, it's O1 to get there. So to find that particular index is just O1. It's very fast, but it's an average of n divided by 2 to rearrange the whole list. So this is the other type of list that you can have. So this is called a linked list. So it's a linked list data structure. And notice that there's no index. The way that they're linked together, so we've got the values at the top, and then you've got 2 variables. I've got a next, for each object, I've got a next variable and a previous variable. So the next variable tells me what is the next element in the data structure, and the previous variable here tells me what's the previous element in the data structure. Obviously, if it's the first element, then it's not. There's nothing previous. So it's a very simple data structure that just links elements together without an index. It's called a linked list, but it's also called a doubly linked list. There are other types of linked lists. For example, there's a single linked list, which is used in table data structures, I think. So we'll have a look at that. We'll be looking at I think when we look at maps, I think we'll see a singly linked list. The linked list for the list interface is a doubly linked list of nodes with a value and also references to next and previous nodes. So get set element run in linear time. So if you want to get any element, what the Java runtime environment has to do is it has to go to each element and check whether or not it's the element that it's looking for. Because there's no index, there's no way for it to know whether or not this element is the element that it's looking for. It goes to the first element. It says, is it the element that I want? No. Is this the element? No. Is this element? Yes. It's found it, then it does something with it. That's why doing these operations is a lot slower than using an array list. So things like getting an element, setting an element, run in linear time, or n, for a list of size n, whereas adding, removing at head or tail run in constant time. So if you want to add or remove an element, whether it's at head or tail, then you run in constant time or 1. So it's very easy to find the head and tail. You just jump to the head and tail and you add elements or remove elements. So if you've got some kind of a problem where you know you're adding or removing elements a lot, then this might be a useful data structure to do it, as long as it's okay for you to be adding things either at the head or the tail. Insertion or removal elsewhere is an average n divided by 2 to get there, and O1 to rearrange the list. So rearranging the list, so if you jump to here, to the middle of the list, getting there, first of all, is an average of n divided by 2, depending on the size of the list. So when you get to the place where you want to add something, then it's very easy to add it, because all you have to do is break these links here. You add the new element into here. Okay, so it's a very fast operation as well. So we say that insertion or removal is a very fast operation. So if you're doing it at the head or the tail, it's O1. If you're doing it elsewhere, then it's average of n divided by 2 to get to that point, and then O1 to rearrange the list itself. So that's how linked lists work. So hashtable data structures are quite commonly used in order to organize certain data structures, like maps, for example, and sets. So let's just have a look at how these operate. So this is what a hashtable array looks like. It's basically, it's kind of a sophisticated type of index in which to order objects. That's basically what a hash table is. You've got the hash table array, and then linked to each index within the array are the elements themselves. So each index within the array contains within it the possibility of having more than one element. So that's where the sophistication comes in. So whereas within a linked list data structure or an array list data structure, an ordered list that has an index, you can only have one element per index. Here you can have multiple elements per index. So it gives it an additional level of flexibility. So for example, so here you see that index value number 0, we've got 2 elements. We've got this element here, and we've got this element here. And you see that these 2 elements are linked as a singly linked list. So each element specifies what's the next element within the data structure. Okay, so we've got this next variable, we've got the value itself, which is the object, and then the next tells me what's the next element, so you can find it and you can compare to it and see if it's one of the elements that you're looking for. Each linked list of elements within each index, we call these buckets. Okay, so you might come across this terminology just so you're familiar with it. So this is a bucket, this is a bucket, this is a bucket, and a bucket can have 1 or more elements in it, or 0 elements, even if there's nothing that's been indexed to that particular that hash table value. So this is how a set, for example, a hash set will be organized. For a map, the node value is a combination of the key and the value. Okay, so instead of the value, you basically got both of them there. You've got the full map value there, and it's organized in the same way. The only difference is that instead of value on its own, you have the key value for the map. Okay, so a hash table uses an object's hash code to index into an array, and allocates objects to a particular bucket. Okay, and the main data structures that make use of a hash table array are the HashSet and the HashMap classes. And for an array of size m, so this is a key thing here. So the first thing that needs to be done is decide what is the size of the array of your hash table. And so I think this is all done. I think you have some control of it, so you can decide that yourself, but it's something that's resizable as well. I think it's something that can be done by the runtime environment automatically for you. And the size of your hash table array is key for things like performance. You don't want it to be too large. If you know you're only going to have a few elements within your data structure, then it wants to be small because you want to use as small a memory as possible. If on the other hand you want it to be large, then that needs to be specified. You know, for example, that you're going to have lots of elements inside it. And if you set your hash table array size to be too small, what happens is that the bucket sizes get larger and larger. So you have more and more objects that map to each index. And that slows down the performance of the hash table data structure. In an ideal hash table data structure, the absolute ideal hash table data structure, each hash table index maps to exactly one value only. Okay, so that's a very, very fast hash table. It's as fast as an array list. It just looks up the index and finds the element straight away. So it's very, very fast in that case. If you have on the other hand buckets that look like this, where you have multiple elements that are mapping to each index, then what happens is it looks up, in this case, it looks up element number 0 and it finds 2 elements. So now it needs to figure out which is the one that I want. So it has to look at each one individually, just like we do in the linked list. It compares, it looks at each one and says, is this the value that I want? Eventually it finds it and it returns it. So it's a slower process finding the element that you want. So the key here is the size of the hash table array. If it's too small, then you're going to end up with a situation where you've got lots of elements mapping to the same index. If it's large enough, however, then that should happen a lot rarer. So this is how we map each value to the hash table index, and it's based on the hash code of the objects. So what you do is you need to override your hash value method, which exists in the object class. So remember, all classes extend the object class, which has this hash value method. So you need to override it and decide what's the hash code for your object. The way this works is your object's hash code is we use this operator here. It's the modulo operator. It returns the remainder from a division. So it's the modulo of the size of this hash table array, in whatever the size is. So in this case, let's assume we've set the size to be 4. Okay. So if my hash value of my object is 12, then modulo the size of my array, which is 4, so it gives you 0. That means that it maps to this location. So, and it's always going to map either to 0, 1, 2, or 3. So that's how the modulo operator works. So if I divide, so any number divided by 4, the remainder will always be 0, 1, or 2, or 3. So that's how the remainder thing works. Okay, so if you, for example, if your hash code is, for example, 15, then modulo 4 gives you 3. Okay, so it goes to here. And then you go full circle again up to element 16, and 16 modulo 4 goes back to 0. Okay, so it's constantly putting things either in 0, 1, 2, and 3, no matter what the number is. So that's why the modulo operator is useful in that way. So equals and hash code must be consistent, otherwise equal objects hash to different positions. So that's why we have the equals contract. So whenever you override equals to define how two objects are equal based on their member fields, their state variables, you need to use the exact state variables to generate the hash code. So they need to be compatible with each other. If you override equals, always override hash code, and hash code is used to index your objects to the hash table array indexes. Okay, so assuming few hash code collisions. So a hash code collision is when you have more than one element in a bucket. So that's called a collision. So the more elements you have within a particular bucket, you end up with more collisions. So assuming few hash code collisions, add, remove, contains, and get are all O1 operations. So it's meant to be a very fast data structure. So you want to reduce the collisions as much as possible. The hash table data structure is, I think it's the default data structure that's used for sets and maps. But if you want things to be ordered, then you would use a tree data structure. So you also can have tree sets and you can have tree maps. Tree data structure is basically a balanced tree. It's a self-organizing tree, automatically organized for you in the background. And obviously that takes some resources and space and memory, so it's a weaker performance than what you get for the hash table data structure, but it's still quite good, and you only use it if you want things to be ordered. Okay, so a balanced tree. So this is what it looks like. So you have a balanced tree of nodes according to their natural order. The data structures that make use of a balanced tree are the TreeSet and the TreeMap. So adding, removing, contains, and get are all their performance is all log n, which is quite good. So for n nodes. So if you've got 1,000, and let's say you've got 1,024 elements within your data structure. So whenever you're trying to add an element, remove an element, contains, or get an element. So to get an element, what you're doing is you start at the center of the tree. So you compare, you say, is this element larger or greater than this element? If it's larger, you go this way. If it's smaller, you go this way. So you only have two options. So that's why the base is 2. If it's larger, you go to node F in this case, and let's say it's J that we're looking for. Okay, so it compares it to this node here. It turns out that it's larger. Finds node J. So it's only taken 2 operations essentially. So it's taken 2 operations to find node J, because it's very efficient that way. So the performance is what we call log n. To find any element, it's 2 to the power of 10. So it's taken us 10 operations to find any element if you have 1,024 operations. So that's what a log n basically. It's if you have 2,048 elements, so it's 2,048 is basically 2 to the power of 11. So you notice that we've doubled the size of our data structure, and it's only taken 1 additional operation to do anything within that data structure. So to see how efficient a binary tree is, it's extremely efficient. So again, if you double it again to 4,096, that's 2 to the power of 12. So it takes us 12 operations to find any element, remove any element, do anything with any element within a tree data structure. So a log-in performance is considered to be a very good performance. So it's an excellent performance, and it's used. That's why it's used, and that's why it's not obviously as good as a hash table data structure where you've got O1 for any operation if you have no collisions. But if you want things to be ordered, then a log performance is a very good performance as well. So it's only slightly worse than O1. So the comparison method must be consistent with equals to guarantee no duplicate objects. And obviously it requires more space than a hash table, because we need to maintain the ordering of the objects somehow. So we need some variables to do that. So it takes a bit more space, and it's a slightly worse performance only. The recommended primary implementations are: for sets, you use a HashSet. For a list, use an array list, and use a HashMap for mash. So those are the default ones. But you also need to think about your data structure and what's most appropriate for it. So don't just use them. Think about if they're appropriate or not. If you don't want to think, then go ahead and just use them. But in most cases, you need to think about your data structure. Linked list also implements list. It also implements queues. TreeSet implements sorted set, and TreeMap implements the sorted map interfaces. So the recommendation is do not use vector or hash table, because they always incur a synchronization overhead. So these are legacy data structures, and you only want to use them if you find some legacy code that already has them. So in that case, you're forced to use them, but don't just use them yourself. There are better data structures than that. And always remember, good advice, program to the interfaces. So we have an arrays utility class, and we have a collections utility class. So the arrays utility class provides a bunch of static methods to do things like search, sort, fill. So an array plus the asList method that returns a list view of an array as well. So there are various useful things that you can do. So you can convert an array to a list. To see more details on what you can do, so have a look at these Java docs for details. Obviously, this is stuff that you don't need to memorize, but it's useful to know where to find the resources if you need to do your coursework, for example. The collections utility class also provides static methods to do things like searching, sorting, shuffling, finding the maximum and min values, etc. So again, have a look at these documentations to see all the different types of methods that you might want to use. So the collections utilities class also provides static factory methods to wrap collections to constrain their behavior. For example, you can provide a wrapper to include unmodifiable and thread-safe versions of collections and maps. So you might want to make your data structure unmodifiable. You don't want anybody to be able to add or remove elements from your data structure. So you can do that. So there's a static method to do that. So an unmodifiable data structure is one where you can't add or remove elements, but the elements themselves, the objects themselves, obviously they can be changed unless you constrain behavior of the particular object to be immutable, that you can't change each. So if you create a class and you create the objects in such a way that it can't be changed once you create it, then yes, the objects themselves will be unmodifiable. But the collections wrapper itself can't do that for you. It can only make it unmodifiable in the sense that you can't add or remove elements once it's created. You can also create thread-safe versions of a collection, which means that you're controlling access to your objects in such a way that you only allow sequential access.